And so we're off and running on the muscular system. Um, your chapter starts off defining things called prime movers, agonists, antagonists. That this is just language, just vocabulary. It's not difficult to understand at all. So I'll try to start at the same place your book does and just define some of this stuff for you. So muscles oftentimes, let me get my black pen up. I think it's currently on red. Muscles oftentimes occur in pair arrangements. They're not always just two. Sometimes there's three or four, but very typically, and I'll tell you what I mean by pair arrangements. There's typically one muscle called a prime mover, and in parentheses, I'm going to write agonist, same thing. And that would be a muscle that typically causes something to move at the insertion end. I'll define origin and insertion again in a minute. I'm trying to go in the order of your book. So, and that's usually oftentimes coupled with something called an antagonist muscle. And we often see a prime mover and an antagonist working in tandem with each other. Classic example that I can give you is the biceps brachii. And I know most people know where the biceps muscle is. That's the muscle that's on the anterior part of your upper arm. You can touch it with your finger very easily. And when you flex, do a flexing motion at your elbow, you flex your forearm, it's the biceps brachii that's causing that movement. That would be considered the prime mover or agonist because it does the moving of the forearm. At the same time, on the back side, the posterior side of your upper arm is a muscle called the triceps brachii. And that's oftentimes during prime moving, the antagonist gets stretched and sort of opposes the movement of the prime mover. So just imagine when you bend your arm at the elbow, the biceps brachii bulges because that's pulling on your forearm. That's the prime mover. The triceps brachii on the backside of your upper arm gets stretched during that movement around your elbow and your upper arm. And then to extend your forearm at the elbow to go in the opposite direction, it's the triceps brachii that contracts, and the biceps then sort of resists or relaxes back to original state. There's also a couple more definitions in your book. Well, let me talk about these prime movers and agonists. I'll say a few more things before I move on. These are usually located on opposite sides of a bone or joint. As in the biceps brachii and triceps brachii example. And then there are also muscles that are classified as synergists. That's synergists. These are not necessarily prime movers or antagonists. What a synergist is, they typically contract during the prime mover contraction to stabilize a joint or aid in the prime movers moving. So I'm going to say contract. Sorry, my board is moving on me. Contract to stabilize joint and or assist the prime mover, the agonist, in its contraction. Classic example would be when you flex your elbow, when that biceps brachii contracts, there are other muscles in your forearm, at your wrist, that stabilize. So your wrist isn't flopping all around, nor is your elbow. It's only moving in one plane, in one direction. It's not moving in multiple planes of space. So synergists are stabilizing muscles, typically close to the located close to the prime mover, and they help assist in that movement. And finally, there are muscles called fixators. These are oftentimes located close to the origin, which I'll talk about in a minute, which is why I don't like the sequence of events in this particular chapter, this author that you have. I would have defined this earlier for you, but nevertheless, I'm trying to be consistent with your book. Fixators are typically close to the origin. They're just a different type of muscle that typically stabilize that point of origin. Keep it from moving. All right, let's move on. Next in your book, the second topic is how a skeletal muscle is named. So I'm just going to write naming skeletal muscles. And there are 7 criteria for naming skeletal muscles. Now, no muscle that I'm aware of, and I'm pretty certain of this, includes all 7 criteria in its name. What it means is there's a list of 7 things of how muscles are named, and most muscles use 2 or possibly 3 of those things in their name. So this is an old acronym that when I was a student, my friends and I came up with how to learn these 7 criteria and know them. And so I teach my students capital S, capital L, L, capital D, A. Doesn't really spell anything, and then the pound sign. So SSLLDA pound is those represent the 7 criteria. Now I'm going to list them all. So the first capital S stands for size of the muscle. Some muscles within their names, the size of the muscle is referred to. Classic examples of that would be words like, these are Latin words, by the way, but you'll get the picture. Longus means that it's a long muscle. Brevis typically means it's short. Maximus means big. Minimus means small. So these names, these words, these designations show up in some muscle names, and it refers to the size of the muscle. The second capital S refers to the shape of the muscle. So some muscles in their name, there's a word that refers to its shape, or the name, if it's a singular word, the one word name refers to its shape. Classic examples of this would be things like the deltoid muscle. That's the shoulder muscle, deltoid. That's the triangular muscle that sits on top of our shoulder. And that, believe it or not, it gets its name for its shape. It is a triangle shape. And guess what? In the Greek alphabet, delta, the letter delta is a triangle. So that's why it's called the deltoid muscle. Another classic example would be the trapezoid muscle. Or sorry, trapezius, getting ahead of myself because it's trapezoid shaped. So let me write trapezius. The trapezius muscle is this diamond-shaped muscle on our back. So if this is the neck where the head meets the body, the trapezius looks like this. It's sort of this big diamond-shaped muscle. It gets its name because it's trapezoid-shaped. So those are examples of shape. That first L stands for location of muscle. Some muscle names have their location on the body or within the body in the name itself. Examples of this would be things like brachii means upper arm. Abdominis means in the abdomen. That's supposed to be an eye. Femoris would be close to the femur. Tibialis would be close to the tibia, things like that. So that's telling us where the muscle's located. Second L is also location, but it stands for the location of origins and insertions. Those are connection points to bones. So some muscles, in their name, it tells us where the locations of their origins and insertions are. All books use this one as a classic example. The sternocleidomastoid muscle. It's a mouthful, but those words tell us exactly where it's located. The sternum and clavicle are the origin of that muscle. That's one connection point. And the mastoid process of the temporal bone right behind the ear is where its insertion is. So that's SSLL. We still have DA and pound. So D stands for direction of fibers. And sometimes it also refers to the direction of the fascicles. Words like, I'll give you examples, words like rectus, R-E-C-T-U-S. Rectus means that the fiber, the direction of fibers is parallel with the midline of the body, what you and I would call vertical or up and down. Then there's words such as transversus, which are the opposite. That means horizontal or transverse to the midline. And words like oblique. That means diagonal direction of fibers. So it's SSLLDA. A stands for action of muscle. Some muscles have in their name the action that that muscle performs. That would be words like flexor, extensor. These are words found in some muscle names. Pound sign, really means number. So I'm going to write, this is represents the number of origins. Not origins and insertions, just origins. Examples of that would be words like biceps, because the biceps brachii muscle has 2 origins. The triceps brachii muscle has 3 origins. So to give you a full example here, so that muscle that I was talking about just a minute ago, the biceps brachii in our upper arm, this muscle, both of its names, that refers to the number of origins, and brachii means upper arm. So it tells us where the location is in the human body. All right, that's basically all muscles, skeletal muscles in the human body use some combination of these 7 criteria in their name. Next on our list, a new topic, we're going to talk about fascicle arrangement and how that relates to function, form and function. Remember what a fascicle is. It's a bundle of fibers wrapped in perimysium. So to start off with first, fascicles, the fibers within a fascicle are all parallel to each other. I'm just writing fibers within fascicles. They sit parallel, but then individual fascicles might not be parallel to themselves. And we're gonna go with the classifications that this book goes with. So I'm gonna hit a new white page. I'm still under fascicle arrangement, and your book divides these into 5 different categories. So I'm gonna use lowercase letters. These are types of fascicle arrangement. I'm trying to go in the order of your book. I usually lecture this in a different order. Circular refers to there's a circular arrangement of fascicles. And so we call the whole muscle actually circular. So the fascicles do this. They don't coil like a spring, but they tend to make a circular shaped muscle. The muscle located around our mouths, the orbicularis oris, and the orbicularis oculi around our eyes. The orbicularis oris is found encircling the mouth, so the lips would be right in here. And the orbicularis oculi are muscles that encircle each eye. That's a U, O-C-U-L-I. So those are classic examples of circular fascicle arrangement. The second type, your book calls convergent. Technically, there's two subcategories to that one, but I'll just leave it with what your book says, convergent. And that, just like the name says, the fascicles usually converge into some sort of major central tendon. So I'm going to draw a big tendon here. I know I'm drawing my fascicles in it. They're converging onto this sort of central tendon. It's an attachment point. And so our fascicles are all converging into one end. They tend to be triangular in shape. This would be, along here would be attachment to bone. And then this tendon would also typically, I'm drawing the pectoralis, major muscle, by the way. So there's the greater tubercle of the humerus. So you get the picture, the convergent arrangement of fascicles gives it its name. The classic example here is pectoralis major, the muscle on the chest. Letter C. This is just a different arrangement of fascicles, that's all. Fusiform. And fusiform, that's what you and I typically think of, at least me, I shouldn't speak for you. That's what I think of when it's the fibers, or the fascicles, sorry, are almost perfectly parallel, but there's a bulging center like this. And then tendon attachments at both ends. And it's usually a flat tendon attachment at the end of these fusiforms. So there's this bulging belly in the center of the muscle. Classic example of this is the biceps brachii in the upper arm. Okay, that takes care of circular, convergent, and fusiform. I'm going to go to a new page and put my letter D. Parallel is similar to fusiform, only there is not that bulging belly in the center. So here the fibers and fascicles are perfectly parallel with the axis, the longitudinal axis of the muscle itself. So those tend to look pretty straight and regularly arranged like this. There's no bulging belly in the center. And these also tend to have flat-like tendons on each end. Classic example of parallel is the sartorius muscle. That's the one I use anyway. There are others. The sartorius is a band of muscle, just so you know real fast. I'm just going to draw a leg. There's the knee. So the sartorius muscle runs from up here, the front of the iliac crest, sort of diagonally across our thigh, the anterior part of our thigh, like this. Letter E in your book is, well, they use E, F, and G as pennate muscles. So I'm going to write the word pennate. And then I'm going to describe, there's three subcategories to the pennate category. So let me these typically are short muscles with short tendons. They tend to be much shorter than parallel convergent. So I'm just going to write the word short. I also describe to students, because it helps me remember this as well, they tend to be, I'm writing feather-like in their appearance, not so much in their function, obviously, but in their appearance. So there's a tendon that extends the length of the muscle in these. Let me write that. And there's 3 subcategories to pennate. I'm just going to write one, unipennate. I'll describe what that is, just to cut to the chase. There's uni, bipennate, and then multipennate. So unipennate just means this, is that there's a central tendon extending the length of the muscle. That's what I'm drawing in dark black here. And then the fibers and fascicles, the fascicles sort of emanate from one side of that central tendon. And this describes or looks like sort of a half of a feather, half of a bird's feather. So that would be unipennate. Bipennate is just the fascicles extend from both sides of that central tendon. I'll try to be quick here. And that gives a true feather-like appearance. I can give you some examples of these. I'll think of some examples. Unipennate, there's a classic muscle called the extensor digitorum longus. It's in the lower leg on the lateral side, the outside of the center. So let me write that, extensor. That's telling what it does, so that's part of its name. Digitorum is telling us it's near our digits or where it inserts. Longus, it's long. The bipennate classic example is the rectus femoris, right on top of your thigh, on the anterior portion of your thigh. Rectus means the fibers, and technically the fibers aren't in perfect line with the midline, but rectus femoris, that's telling us its location on top of the femur. Now I'm going to go to multipennate. I need to call up a new page for that. So number 3, subcategory. That's multipennate. And here's what these look like. The tendon arrangement, there's typically tends to be one large, really big tendon that sort of branches out like a tree, like this, and they're oftentimes triangular as well. And then there are fascicles arranged around each of these branched tendons. And this one in particular, oftentimes these multipennate tend to make a triangular shape, but they're 3-dimensional. They're not as flat as just a pure triangular or convergent. This classic example would be something like the deltoid over your shoulder. The deltoid muscle, this end of the deltoid attaches to the scapula and clavicle on top, way on top of your shoulder. And then this really big tendon, it wraps and goes all the way down to that deltoid tuberosity on the diaphysis of the humerus. All right, so that describes fascicle arrangement. Now we need to, please don't get intimidated by this. I need to use some terms that are used in basic physics. This isn't a physics class, so I don't really like physics either, and I'm not gonna get into complicated physics, but we need to use this language in order to describe levers and fulcrums and efforts and things like that. So I want to use the rest of this whiteboard and just start this conversation as bones act as levers, And then fulcrums, sorry, it's Fulcrum, are typically the joints. And what a fulcrum is, it's a fixed point that something moves around. That's what the word means. And levers are just something that's moved. They're typically some sort of hard substance, aka bones in the human body, that are moved. And then this term, effort, is what does the moving. And this is from muscle contraction. So these three words, levers, fulcrums, and effort. Effort refers to actual muscle contraction. Levers refer to the bones that are being moved. And fulcrums are the fixed point which the movement either radiates or moves around. And those are, in the body, those are represented by joints. There's also two terms called mechanical advantage and mechanical disadvantage. I'll describe what those two terms mean. These are in your book as well, so let's define them. So something that is a mechanical advantage is when the load, typically, when a load, that's something that's being moved, and when that load is close to the fulcrum, that's called mechanical advantage. When the effort is close to the fulcrum and the load is far away from the fulcrum, I'm going to draw pictures on the next page, don't worry. That's called mechanical disadvantage. So let's do a picture of this. If we have a situation where I'm just going to draw, for example, a seesaw that children play on. Let's just say we put a big weight on this end, a rock or a big heavy weight, that would be the load that has to be moved. The fulcrum is the point at which the movement revolves around, and then the effort is what we have to do in order to move the load. What mechanical advantage and disadvantage refer to is the closer we put the load to the fulcrum, the more advantageous that is, the easier it is to move. But the opposite is also true. So this would be advantage, a mechanical advantage, if we move the load further away from the fulcrum so that the effort is closer to the fulcrum than the load. If we put the load all the way out here, that becomes disadvantage and very difficult to move the further away you move it. All right, so that defines that. Now, there are three categories, basically, of levers. And I'm going to define them and then give you examples in the human body. What the criteria for defining these three categories is basically the position of the fulcrum, this thing, relating to the effort and the load. If we move things around, that defines what category a lever is. So I'm just going to label these number one, a first class lever. First, I'll define it for you, then I'll give you an example. A first class lever is when the fulcrum is between the effort and the load, just like I drew above. So I'm going to write F is between the effort and the load. A classic example is this one. This can be a mechanical advantage or disadvantage, like we saw up here, based on where we position the load and the effort in relating to that fulcrum. So, so an example, I'll give you a human example in a moment, but I'm going to write advantage or mechanical disadvantage, depending, I'll say position of E and L to F. So the further away L gets becomes a disadvantage, and the closer that E gets, that's also disadvantage. The further away E gets in this direction and the closer L gets to F, that becomes advantageous. Now, an example, a human example, these are not very common in the human body, this type of category of lever. The classic example is the head sitting atop or on C1 atlas, that first cervical vertebrae. So we have, I'm just going to draw a vertebrae right here, C1 from a lateral view. The occipital condyles on the occipital bone sit in there. There's the skull. The muscles, which would be the effort on the back of our head and down the posterior side of those cervical vertebrae, are the effort. And the fulcrum is this point that rocks on that C1 vertebrae. This allows us to nod our heads yes, by the way. So that would be the fulcrum. And then the load is the weight of the head, mostly the front of the skull. So this would be the load. So there's a classic example of a first-class lever in which the fulcrum is located between the effort and the load. Second type is called a second-class lever. These are also very rare in the human body. In this, the load L, the load is between the fulcrum and effort. The example outside of the human body would be a wheelbarrow. So if I have a wheelbarrow, I'm going to draw it really quickly. And there's an axle with the wheel. And I put something in here. The effort, here's the load, what we're carrying inside of the wheelbarrow. And it's located between the fulcrum, which is the wheel. That's the point at which things revolve around when you lift. And the effort would be a person on this end, the handle end, actually lifting the load on the wheelbarrow. These are quite uncommon in the human body, so I'm just going to write. But there is a classic example that we can give in the human body, and that is when we stand on our toes. This is an example of a second-class lever, and I'll explain to you how that works. So I'm drawing a side view, a lateral view of the calf. There's the shin. When we stand on our toes, I'm just going to draw an arrow up to imply that we have gone from the heel off the ground to stand on our toes. The effort is located up here. That's produced by muscle contraction of these muscles in the calf muscles here. The load is actually the entire weight of the human body that's centered around, mostly around the ankle here. And then the fulcrum is the ball of the foot right here that we're actually moving around. So we're moving the heel around this fulcrum point, which is the ball of the foot. That becomes the fulcrum. Last but not least is a third class lever. Most joints and muscles and levers in the human body act as third class levers. In this, I'll define it for you. The effort lies between fulcrum and load. So this is the most common type in the human body, not outside of the body per se. So most common type in the body, and it always produces mechanical disadvantage. That doesn't sound very good for you and me. I'm trying to write advantage, holding this plastic pen with the tips of my fingers on a glass board. It's a challenge. It always produces mechanical disadvantage, but there's a trade-off. So it's hard, things are harder to move, but the trade-off is it increases class 3 levers, increase speed, which is good for us, and mobility. So those are two good things. So that range of motion is what I'm going to put, that's what's increased with class 3 levers. But their mechanical disadvantage just means it's harder to pull them. So I'm going to try to give you an example. Most books give this example as an out-of-body example. I don't really like it. A pair of forceps or tweezers. I'm going to give you the real-life example in the human body, and that let's just do the biceps brachii. This is the most common, but this is also, if I draw a picture, I'm going to draw an arm. There's the elbow, an arm flexing. When that happens, the biceps brachii bulges a little bit. I'm just going to draw a thumb, and let's put the hand out, and we can even put something in the hand that weighs. So we've increased the load. The load would actually, the load is the bones in the forearm, the weight of the forearm, as well as the weight of this item that we are holding. And when we flex, we move around a fulcrum point, which is the hinge of the radius and ulna with the humerus right here at the elbow. So this is the fulcrum. Now you may be thinking the biceps brachii is the load, or sorry, the biceps brachii is the effort, which is true. It's up here. And that doesn't look like that it's between the fulcrum and the load, but technically it is. The tendon of the insertion tendon of the biceps brachii is actually on the radial tuberosity right here. So this point, I'll circle it in blue. That is where the effort is focused. So the effort is actually between F and L. That makes more effort required in order to move that lever, but it also increases speed and range of motion. That was the most complicated part of this chapter. Now I'm going to talk about a few extra things before we call it a day. It'll be short lecture day, which is good. A muscle, when it contracts, typically contracts to roughly 70% of its original resting state. Or resting length. That means you could flip that on its head and say a muscle actually shortens about 30%. So long fibers in longer muscles versus short fibers do not really affect the power that's generated during muscle contraction. Long fibers tend to increase range of motion and sometimes speed, depending on the lever. But long fibers definitely increase range of motion. I'm going to say no effect, no net effect on increasing power. The power of a muscle contraction depends on the total cross-sectional area. I'll describe that after I write this. Power of contraction is dependent not on length of fibers or even the length of the muscle. It's dependent on the cross-sectional area of the muscle. Think of that. That's a fancy way of just saying the diameter of the muscle. So when we slice it, the larger in diameter the muscle tissue is, the more power it can generate. So a short fiber can contract just as forcefully as a long one, but more fibers in that cross-sectional area or diameter is what increases the power. I'm making sure that I've covered everything I wanted to for today. I want to talk about origins versus insertions. And I don't know if Eric is here today. I think he asked a question about direct and indirect connections. I'm going to talk about that briefly before we leave. So let's do this. Origins versus insertions. These words, origins and insertions, just refer to the point where muscles connect to bone. And they're typically on opposite ends, not always, but they're typically on opposite ends of the muscle. Origins, I'll describe them first, are connection points I'll remind you, since I didn't write this out, muscle to bone. When the muscle contracts, there is no movement at that end. So whenever you see the word origin, think connection point where there's no movement. Insertion, on the other hand, that's I-N-S-E-R-T-I-O-N, is the connection point where when the muscle contracts, there is movement. So I'm just writing is movement during contraction. So let's do our biceps brachii example. The shoulder, this is a side view. There's the arm. Let's flex the forearm. Biceps brachii muscle bulges when it contracts. There's the hand. This muscle, the biceps brachii, is here on the anterior part of the upper arm. Its origins, there's two, are on the scapula back here. The insertion is on the radial tube. So I lost connection for a minute. Are you guys still there?
Yes.
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 Okay, sorry guys. Did I black out on you?
Yes.
Okay, yeah, my screen went totally black for a minute and it said reconnecting. So let me just,
Yeah,
I'm
you
almost,
froze. You just froze.
yeah, okay, I'm almost finished. My iPad's got plenty of power left in it, so I don't know what's going on, but I'll try to be quick to finish up here. We were talking about origin insertion. Just let me say a few more things and we'll call it a day. The origins tend to be, let me get my black pencil back. I'll just write O for origins. These tend to be proximal to insertions. Insertions tend to be distal. That means further away. Insertions are further away from the body, typically, and origins are closer to the body or midline of the body. So, and this is almost invariably true. And also, when the muscles contract, they pull the distal end, that's where there's movement, toward the origin end. So we always go for, as a pulling action, from further away from the body toward the midline of the body, somehow, some way. That's how they work. And finally, these two origin inserts, the muscles that are involved with movement, never is a strong word, so I'm going to say almost never, cover the surface of what they are pulling. So, classic example again, when you flex your forearm at the elbow, your biceps brachii is actually pulling on your forearm. It doesn't cover your radius and ulna, though. It doesn't cover your forearm. It covers your humerus. So the muscles almost never are, they're in contact with the lever with what they're pulling, but they don't actually cover it. And finally, I did want to go over, because there was a question last week, direct versus an indirect muscle attachment. This is a complicated, can be a complicated topic, and it's been misused. So direct versus indirect. The true, I'll write connections to bone. The true definition of this, scientific definition, is what is not, unfortunately, is not what is being used. Literally, a direct connection of a muscle to a bone refers to if the connective tissue from the muscle attaches directly to bone surface. Okay, so I'm just going to write connection directly to bone surface. An indirect, this is the strict scientific definition. An indirect attachment means the connection from the muscle attaches to the periosteum of the bone. So here's an example. In a direct attachment, I'm going to draw the head of the femur. There's the neck, there's the head of the femur. On this femur, there's a periosteum, I'll make it in green, that sort of covers the diaphysis of this bone. Now, muscles that attach directly to, say, the greater trochanter via their tendons, like let me draw the greater trochanter. If this is the backside of the bone, there's the greater trochanter, there's the lesser trochanter. Muscles that attach directly to bone surface, like the one I'm drawing, are called, scientifically are known as direct attachments. An indirect attachment would be if a muscle attaches to this periosteum that the bone has wrapped around it. So the muscles that I'm drawing down here are really attaching to that green connective tissue. So that's indirect and that's direct, because it's direct. Indirect, this tendon is attaching directly to bone surface. Now these two terms have been somewhat changed and misused. You may read either on the internet or in some textbooks that it refers to whether or not a muscle is attached by a tendon. Technically, that's incorrect, but I'm going to describe that to you. Some books say that direct means no tendon attachment is used. And so the muscle attaches directly, not via an organized tendon. An indirect would be if there is a true tendon attaching to the bone. I prefer the literal scientific definitions, these two. So that's how I recommend you learn this. A direct attachment is the connection. Doesn't matter if it's a tendon, an aponeuroses, or what the actual connective tissue is from the muscle, but that connection is directly on bone surface. An indirect connection is when the connection from the muscle, be it a tendon, aponeuroses, or some sort of epi or perimysium, is actually attaching to the periosteum of bone tissue, not directly onto the surface of it. All right, I'm going to stop my recording here.